Hey, there it is. All right. So, acids and bases is our next chapter. So we're going to talk about chapter 10 here, which is acids and bases. It's our last general chemistry sort of chapter before we go into organic. Nice excitement. I like it to get excitement. All right, so let's get into acids and bases before it changes his mind and wants to shut down again. All right, so before we get too far, just very quickly in terms of acids, how to name acids, just so you have an idea when you look at an acid, what it is, or how you go about naming it. What makes something an acid, as we'll talk about, is basically has an H plus, is really the cation in all acids. And when you go to name an acid, it really involves basically oxygen. And if your acid does not have oxygen, then the way we name it is we start with hydro something ic acid. So for example, HCl, Cl is chloride, that is an acid, and there's no oxygen. This would be hydrochloric acid. You have HBr. It also has no oxygen. This would be the missing part is the negative guy here, which would be H plus and Br minus. This would be hydrobromic acid. So if you have an acid and it does not have oxygen in it, it starts with hydro, it ends with ic. The middle part's really the anion or negative guy there when you go to name it. Now, you may be asking, isn't this just hydrogen chloride? And the answer is yes, if it's a gas. But if it is aqueous here, like a solution, has the AQ symbol next to it, that usually will make it an acid when we're talking about these guys, and we would name it in the acid form there rather than if it was a gas, then it would be hydrogen chloride gas. If it does have oxygen, it will contain one of those polyatomic ions. And those polyatomic ions, as we've talked about, and usually in one of two ways, ate or ite. And if your polyatomic ion ends in ate, your acid would be something ic acid. So if you had HNO3, NO3 is nitrate, ATE. This guy would be nitric acid. If you had H2SO4, SO4 is sulfate. This will be sulfuric acid. Now, if your acid contains a polyatomic ion and has oxygen, I'll come this way, and it is ITE the way it ends, then the acid is something OUS acid. So HNO2. NO2 is NO2 minus, that is nitrite, ITE. This acid name would be nitrous acid. If you had H2SO3, SO3 is sulfite. This would be sulfurous acid. So that is how you go about naming acids. It has to do whether or not there's oxygen or no oxygen. And again, if there's no oxygen, that's the one that has the hydro. If it has oxygen, no hydro, yeah, in terms of it. And again, it's based on the polyatomic ion name there. Any questions on that there? All right, in case you ever come across an acid, you hopefully know how to name it, I hope. All right. Let's talk about some characteristics of acids and bases. Acids have sour taste. They do change the color of litmus paper. And typically speaking, if it's acidic, your litmus paper oftentimes will go from blue litmus paper to red. Or basically, if the litmus paper turns red, then it's going to be acidic. It reacts with certain metals to do a single replacement reaction and produce hydrogen gas. So if you took some zinc plus some HCl, hydrochloric acid, it's going to come in and kick out the hydrogen. That's going to make hydrogen gas, some bubbles. And a little zinc chloride will come together here. And a little 2 there. They also can conduct electricity, so there's strong acids and weak acids, and they are strong and weak electrolytes. And electrolytes, as we talked about again, are things that will basically produce ions in solution and produce electricity or conduct electricity. Bases, on the other hand, have a bitter taste. They feel very slippery. A lot of soaps are bases, like drain cleaner and all that kind of stuff. Little Drano and all that kind of things are typically basic. They also turn litmus paper blue. So typically you would use red litmus paper, and if it turns blue, usually blue is the color there for basic. A lot of bases also, there can be strong bases and weak bases as well. And they are electrolytes and can conduct electricity in addition. Now, pretty much an acid has the ability to produce H plus ions in solution. And when we're talking about something being able to be a pretty good acid is it is able to produce free floating, not attached to anybody, H plus ions in solution. And these are sometimes referred to as hydrogen ions. In terms of acid-base chemistry, if you have the hydrogen ion and you have this guy here, which is H3O plus, that's the hydronium ion, it's basically the same deal, yeah. So it is basically the same thing. It is used interchangeable in formulas and also equations. I would say nowadays people in books use H3O plus the most. I personally will use H plus. So wherever I write H plus, you can basically swap it out for H3O plus. That goes for equations and also goes for formulas as well. The hydronium ion and H plus, pretty much the same thing. H plus is also called a proton as well, and that's because hydrogen has one proton, one electron, and no neutrons. And that means in order for it to become positive, it had to lose its electron, which leaves it only a proton. So it's sometimes referred to as a proton and acid-base chemistry. Strong acids, as I mentioned, are strong electrolytes. Be honest with you, there's about 6 strong acids, and those are most of them there. We have our hydrochloric acid, our sulfuric acid, our perchloric acid, our hydrobromic acid, hydriodic acid, and our nitric acid. This 6-pack of acids are pretty much your 6 strong acids that you come across. Sometimes it's good to know those 6 because by process of elimination, you just know that if it's not one of those 6, it's probably a weak acid, to be truthfully honest with you. So, these 6 are really strong ones. That means when we have something like nitric acid, when it is in solution, it is a strong electrolyte. It is going to 100% break apart into our H plus and nitrate ions, so 100%. So if you dump that into a beaker, you're basically going to have a bunch of H pluses and some nitrates. And this is why this is considered a strong acid, not really for the nitrates, but because when you dump it in there, you've now just jumped up the amount of free H plus in that solution a lot, and that's going to make that solution really, really acidic. And that's because pretty much it's just going to all break apart, no base staying together in that case. And again, it's going to be able to release this hydrogen, this H plus ion, and that again is what makes up an acid. So the ability to do that will make it a really strong acid. Now, bases, on the other hand, typically can produce hydroxide ions in solution, OH minus. It's the same sort of idea when we talk about a base. It's that ability to produce free-floating hydroxide ions in the solution. So free floating around, again, not attached to anything. Strong bases typically will have hydroxide in them. And to be honest with you, if you look on the periodic table, where lithium is, where sodium is, where potassium, and you hang a right, go calcium, strontium, and barium, that kind of up and over and down. All those guys with hydroxide are pretty much your strong bases. And that is because group 1 is the alkali metals, group 2 is the alkaline earth metals, and the word alkaline means basic. Yeah. So that is where a lot of our strong bases come from, basically group 1, group 2, with hydroxide on them. And again, same idea there. If you have something like sodium hydroxide, which is a strong base, that thing is not going to stay together. When it goes for a swim, it's going to break apart completely into these ions. And once again, that's going to do is you will have a lot of sodium ions, but more importantly for the pH, you'll have a bunch of hydroxide ions in that solution really quickly. And again, that's going to make it really, really basic because it's able to produce a bunch of OH minuses. Any questions on that there? Do all bases have hydroxide in the actual formula? The answer is no. There are weak bases, and a lot of weak bases actually produce hydroxide. Probably your most famous weak base is NH3, which is ammonia. That is probably your most popular weak base there. It does not have hydroxide on it, but it can react with water. And when it reacts with water, what it will do is it'll essentially grab an H plus from the water. And the result of that is you'll make some ammonium ion and you will make some hydroxide ion here. So you're able to produce some hydroxide, so it's still considered a base. It is way weaker of a base than sodium hydroxide because all sodium hydroxide has to do is go for a swim. You got a bunch of OH minuses. Ammonia's got to go find a water, do a little reaction, and it's a weak electrolyte, which means it's going to kind of mainly say there it's not going to produce as much hydroxide, but it will still be able to do so. And again, that's why it's still considered a base. Any questions on that there? Now, when we take a reaction of a strong acid with strong base, as we talked about in reactions chapter, that is pretty much the reaction that we always get. We always get basically the formation of water, right? And that was one of the reasons why a reaction took place. And when you take a reaction of a strong acid plus a strong base, you always make basically two things. You make a salt and water. Like if we took HCl, which is a strong acid, plus some sodium hydroxide, which is a strong base, that is a double displacement reaction, right? We're going to switch partners just like so. H and OH, that is how we get our water, right? So that is where our water comes from. And our salt, which is an ionic compound, is the sodium and the chloride coming together in this example. And that would give us our sodium chloride. I guess I should have wrote it the other way there, but that's our water and our salt going in that direction there. And ultimately, what is the overall reaction happening is, as we talked about, is really that H plus from the acid going and finding the OH minus from the base to make water, basically, is the overall reaction that's happening. You could combo any strong acid or strong base together, and that is what you're going to get. You're going to basically get the formation of water. And as we talked about, that really is, again, one of the three reasons why a reaction takes place, right? Making a solid, making water, and electrons being transferred. It ultimately is under that big umbrella of double displacement reactions we talked about, where the two positive guys basically switch partners. Question out there. So again, as you can see there, if you go through really what is happening, again, that formation of water is ultimately what's happening is really that H plus from the acid, finding that OH minus from the base, coming together to make your water in this case. The other guys are what are referred to as spectator ions. The salt, it's just hanging out and not really doing too much other than still floating around the solution. They're actually neutral salt. It won't affect the pH or anything like that of the solution. So they're just kind of floating around really to balance out the charge, but they're not really making anything. It has sodium and the chloride in that solution. Bless you. So again, a couple of other ones here. Here's our water and our salt being formed. Again, our sodium chloride, in this case, our potassium nitrate. Once again, switching partners, going this way and this way, and that is what we get there. I would say in most cases are happy today, the computer, apparently. I think it's like, I don't want to lecture today. All right. So when we have that acid and base, we get the salt. So once you try one, let's say if we took, let's say we took sulfuric acid, and we reacted it with potassium hydroxide, what would be our products that we would make here? So think about what you would get. That's what you think about with acid and bases. So really what we want to think about is just the basic units that make these guys up. For all acids, the positive guy is always H plus. So that's always the positive guy there. That hopefully you could recognize as sulfate. Over here, that is a potassium group 1, and that is hydroxide. So remember, always in these type of reactions, we're just going to swap partners, basically. We know we're going to get water as a result of this here, so that is where water comes from right there, our H2O. And then we do want to put the salt part together correctly, like any ionic compound. That's +1 and -2, which means we do need one more of those guys to give us our proper formula here of K2SO4. At this point, we then want to balance by putting some numbers up in front, maybe over there as well. Looks good, I think. And then we have our balance equation. So really just like those double displacement reactions we talked about in that earlier chapter. Any questions on that? Obviously here we made our water and our salt, right, in this case. And again, a salt's just an ionic compound put together properly here, yes. All right. So the first person to really recognize acid and bases, and he did a lot of work with electrolytes, which again are those guys that dissolve in solution to create ions, was Arrhenius. And again, he basically defined an acid as really anything that can produce an H plus ion in solution, while a base can produce hydroxide, as we've been talking about. And again, as we've been talking about, this should be free ions in solution, and that is what we're looking at, that H plus and that OH minus, again, not attached really to anything. It was a really good definition. As you can see here, if we took some hydrogen chloride gas and bubbled it through water, we actually get the acid here. And again, in that solution, you're going to have a lot of that H plus. Same thing here. We took some sodium hydroxide dissolved in water. We're going to produce that hydroxide ion. And again, that is going to make that obviously an acid for the first one and a base for the second one. Now, it was a good one, but he did a lot of work with bases that have hydroxide in them. And as I talked about a second ago, not all bases actually have hydroxide in them. There are some that can produce hydroxide. So more so when we talk about acid and bases, we talk about sort of what is known as the Bronsted Lowry definition of an acid and base. And the Bronsted Lowry definition of an acid and a base is an acid is a proton donor, and that is somebody that will give away the H plus, and a base is a proton acceptor. That is somebody that will accept the H plus. It's really important to understand that it is not just a hydrogen, but the plus part plays an important role in terms of charges. So when somebody loses a positive charge, they become one more negative, right? They got less protons and more electrons. When somebody gains a positive charge, like a proton, it now becomes one more positive because it now has more protons than it did electrons. So a very common mistake people make is they do the hydrogen part of it, but they forget about the positive charge there. So it does affect the overall charge that's happening. So for example, if we took something like HCl and we showed it dissolving in water, in this case, we will have, this is our acid, and water here will actually act as our base in this case. And what's going to happen is the acid's going to send its H plus over. The result of that is you will actually make H3O plus, and you will be left with Cl minus when it loses the H plus. The consequence of the Bronsted Lowry definition is it actually creates partners on opposite sides of the arrows. So the acid over here on the left is related to the Cl minus over here on the right. This is what is known as is conjugate base. Well, the base here, which is water, its partner on the other side is the H3O plus, and this is what is known as the conjugate acid. So we get these conjugate acid-base pairs as a result of the Bronsted Lowry definition. Now, in order for something to be a pair and to be related to each other, this right here, the H plus, one H plus difference only. So it can only be a difference of one H plus. So when we go from the acid to the conjugate base, it has one less H plus because it gave it away. When we go from the base to the conjugate acid, it has one more H plus because it accepted it. And that can be the only difference between those two things for them to be related to each other. Your regular acids and bases, left-hand side of the arrow. Your conjugate guys, usually right-hand side of the arrow is where you find those guys. And again, just one H plus difference only. We look at something like I wrote earlier with the NH3 and water. The NH3 is actually the base, and water in this case is going to be the acid. It is the water sending the H plus over in this particular case. That is going to form NH4 plus and our OH minus in this case. And here the NH3 is our base. That NH4 plus would be our conjugate. I'll write down here, acid. The water would be our acid, and the OH minus would be our conjugate base in this case. Again, the only difference between those two is one H plus that was transferred. You might also notice water in the first example was a base. Water in the second example was a acid. There are things that can act as an acid or a base. Those are what are referred to as being amphoteric substances. Can act as an acid or a base, and water is an example of that. It could act as an acid or a base. It could even, as we'll talk about shortly, react with itself, where one reacts as an acid and one acts as a base, basically. Any questions on that there? So in general, this is what our sort of equation looks like. Again, this is an acid, which means it's going to send the H plus over. This acid would be related to the conjugate base on the other side. And here's our base that's going to accept it, which would be related to the conjugate acid on the other side. Again, the only difference is the H plus. Also, charge-wise, this guy loses a hydrogen, and it was neutral to begin with. So when it loses a positive, it becomes one more negative. That's why it's -1 on the other side. This is water, which was neutral to start with. When it gains the hydrogen, it also gains the positive charge. So it goes from no charge to +1. So again, the charges do adjust as you kind of get those pairs going on. Questions on that there? Now, again, as you can see, this is the one we just talked about there, our hydrochloric acid. Now, earlier I said sometimes people will use H plus versus H3O plus. Now, what we're really looking at in this equation is just really the strong acid dissolving in water, which you can absolutely, like you did here, put the water into the equation and do it more like a Bronsted Lowry definition. And as you can see, you do produce H3O plus. You could also, for this strong acid or any strong acid, leave the water out of the equation and just have it break apart into H plus and Cl minus. Not necessarily a Bronsted Lowry sort of situation, but here we will get the H plus versus the H3O plus because we left the water out of it, and it's perfectly fine as well. So again, H plus and H3O plus represent really the acid part of the solution. And again, they're used interchangeable. Again, in the case of acids, most people a lot of times will not include the water with the acid sort of breaking apart in water. But if you do, there's nothing wrong with it, and you'll just get the H3O plus versus H plus and stuff like that. Any questions on that? All right, there we go. That's what we're talking about there. So our hydronium, again, it's going to pop off a hydrogen and make our H3O plus in that solution. All right, so I want you to take a moment here for each of these, decide if they represent a conjugate acid base. Okay, so again, what we're looking for in order for these to be partners is this and only this, a difference of 1H plus. So if there's just a difference of 1H plus, then they are related to each other. If there's more than 1H plus difference, then they are not related to each other. So if we look at the first pair here, we got a little HClO4 and a little ClO4 minus. So these two here, the difference between these two is 1H plus. You could get it by removing the H on this side, and also it becomes one more negative. You end up with this guy over here if you do that. So they are partners. So that would be a partner paired there. You could also put the H plus back on this guy, and you should get this guy. Again, should only be one H plus difference between them. How about HClO, HCl, and ClO minus? Difference here is 1H plus, but there's also a difference of oxygen here, no oxygen here. So because of that, not a partner pair. It can only be 1H plus difference, can only be the difference that you see there. Here we have H2PO4 minus and HPO4 2 minus. So the difference between these two is 1H plus. Again, however you want to look at it, you get rid of an H here, leaves you that, and one more H getting rid of, which is a positive, becomes one more negative, and now we got the guy on the right, right? So they are related to each other. And how about the last one? Are they related to each other? They are. Again, the only difference is an H plus. You could take the H off, and then losing the positive makes it one more negative, and you end up with the guy on the right, right? So, or you could put it on the guy on the right. You should end up with the guy on the left, whichever way you want to do it. Any questions on any of those there? What about H2SO4 and SO4 2 minus? Are they partners, pairs? They are not. And they're not because the difference here is not 1H plus, but it's actually 2. Yeah. And this is what is known as a diprotic acid. It has 2 hydrogens that it could give. And hydrogens actually come off of acids one at a time. So what would happen in this case is H2SO4 would lose 1 hydrogen and make this. Then this guy would lose another hydrogen and make this. And that is why H2SO4 and HSO4 minus are partners. Those guys are partners. HSO4 minus and SO4 2 minus are partners. But if you try to jump it there directly, too many steps along the way. So those guys are not partners, but these are partners, and those two guys would be partners as well. Any questions on that? So again, has to be only an H plus difference. If there's any other difference, if there's more than one H plus difference, they are not considered conjugate acid base pairs. Any questions on that one there? Okay. All right, so for each of these, write the conjugate base. Starting with each of these, write the formula of what the conjugate base would be for each of these. Take a few moments and see what you come up with. I want to think about sometimes if you have a question like this is what we talked about where we have an acid and we have a base. And on the other side, we got some conjugate base and conjugate acid. And again, the acid on one side is related to the base on the other. The base on one side is related to the conjugate acid on the other. So in this particular problem, if you are asked to write the conjugate base, you want to end up over here, which means if you just follow this backwards, everything that you are looking at this point is a base. And if you can identify that as being a base, all you have to do is the Bronsted Lowry definition of adding an H plus, right? It's going to accept an H plus. So you should always know in this case, H plus is the deal. You just got to know to put it on or take it off. And in this case, what we would be doing in each of these cases is this is a base. So we're going to, actually, we want the conjugate. We want the conjugate. I know I'm getting there. It's been one of those days. I can see it already. Okay. We'll just cut that out of the video later. It'll be all right. Just be okay. Sorry about that. Should read the question and look at what it says, which is a conjugate base is what we're looking for. So we do want to end up over here at the conjugate base. And that means if we go backwards, each of these things are acids. That seems better. This will actually answer the question it's asking. So what that means is in terms of a Bronsted acid, it's going to actually donate the H plus. So in this case, we would want to take off the H plus. So here, if we take off an H, that leaves me one H and an S. This thing was neutral to start with, so we lose the positive, it becomes one more negative. So it should be HS minus in this case. We then go to HS minus and take off the H. We're left with a sulfur. It already has a -1 charge, so we lost the positive, so it becomes one more negative, ends up at a -2 charge in this case. NH3, we're going to take off a hydrogen. That's going to leave us 2. Again, it was neutral, so when we lose the positive charge, it's going to become one more negative, and it will be NH2 negative. And H2SO3, once again, going to take off one hydrogen, leaves us one hydrogen. Everything else stays the same. Was neutral to start with, becomes one more negative, and we'll end up there. Any questions on any of those there? All right, so dare I try one more here? HSO4 minus. Why don't you write the conjugate acid for it, starting with it? And why don't you also write the conjugate base, starting with that guy? So in each case, you're going to start with that guy, right, with the conjugate base and the conjugate acid. Okay, so let's take a look. We'll start with the conjugate acid this time since I was so anxious to do it last time. So we want to end up here at the conjugate acid. That means now, since we were asked that question, if we go backwards, that means what we're looking at is a base. And again, the definition of a base is it should accept the H plus. So in this case, we're actually going to add the H plus to this, and that will give us H2SO4. Add a hydrogen plus 1 minus 1 gives you 0 when it's all said and done. Now, the conjugate base in this case, just like in the problem here, if we go backwards and think about what we're looking at, that's an acid, which means we're going to take away an H plus in this case, and that will get us SO4 2 minus in this case. Take away the hydrogen, and again, it becomes one more negative in this case. Another example of a substance that is amphoteric, it could act as an acid or a base in this case. Usually things that have a hydrogen, like a negative charge, have the ability to kind of do that, typically speaking. Any questions on conjugate acid base pairs here? So talk a little bit about acid strength. We talked a little bit about it earlier, but we can have, as I mentioned, strong acids and also weak acids. And they really are strong electrolytes and weak electrolytes, like we talked about with electrolytes. If it is a strong acid, it is really going to be a one-way street, like our hydrochloric acid. Everybody is basically just breaking apart. Nobody's staying together. And we're going to get, again, as we talked about earlier, that really influx of H plus into that beaker or solution. And that's going to make it really, really acidic because you're just going to have a lot of H plus very quickly. Now, we could have a weak acid, which, much like we talked about with weak electrolytes, has the arrows heading in both directions. It actually will mainly stay together. So just like a weak electrolyte, most weak electrolytes are weak acids or bases. So if you had something like hydrofluoric acid, it would break apart into H plus and F minus, but it mainly would stay together. And you would have a few of these ions over here in solution. So if you looked at a beaker that had hydrofluoric acid in it, what you would actually mainly see is that whole guy still together, basically floating around. You would have a little bit of H plus and F minus in there. And again, because it's still able to produce some H plus in solution, is considered an acid, but it is nowhere near as strong of an acid as something like hydrochloric acid, which, as I drew earlier, pretty much just going to flood this with H pluses, a lot of them, as it goes for a swim in this case. And again, I think we did that list of the 6 strong acids earlier. And again, those guys essentially will pretty much 100% break apart. Sulfuric acid is a little interesting because it does have 2 hydrogens, but for the most part, you could think of it as just completely breaking apart. Obviously, as I mentioned, if the forward direction predominates with the giant arrow, you have a strong acid, which again will completely ionize or dissociate in water. So basically a fancy way of saying it's just going to completely break apart. It's not going to stay together. And again, if that reverse direction predominates, then you have that reversible weak acid happening. And this also goes, again, like we talked about, for bases as well. So if you have a strong base, it's basically a strong electrolyte. It's going to completely break apart. It's not going to stay together. Something like sodium hydroxide, potassium hydroxide in solution, just going to be fully broken apart into ions. If you have something like that weak base like ammonia, it's going to mainly stay together, but will produce a little bit of hydroxide in that solution. Now, sort of the relationship between acids and bases and their conjugate partners is, if you have an acid and its partner, which is the conjugate base, and if you have a strong acid, its conjugate partner will be relatively weak. So it's kind of an opposite relationship. And if you start with a weak acid, its conjugate partner on the other side will be relatively strong. Now, just to caution you, strong does not mean like it's a strong base or anything like that. It means in the sense that those guys actually do have the ability to continue to react with water that's present. And the effect of it reacting with water is it actually can affect the pH or the acidity of that solution. As an example, and again, you don't have to worry too much about this at all, but if you had HF, which is a weak acid, its conjugate partner or base would be F minus. And F minus, when it's in solution with water, will actually react with water in what's known as a hydrolysis reaction. Will actually poach a H plus right off of water. And the result of that is you'll actually make some more hydrofluoric acid, but you'll actually make some free hydroxide. And that can have an effect on the pH, for example, of the solution, because you're producing that. That doesn't happen when you have like a strong acid like HCl. Its partner would be Cl minus. That Cl minus pretty much will not react with water. It's just going to float around in it. It won't react with water. It won't go through a hydrolysis reaction or produce any H plus or OH minus in that solution. So it really won't affect the solution. Same idea if you had a base and its conjugate acid partner. Same sort of relationship. If you have a strong base, then its conjugate acid, it's a banner day today, conjugate acid there, would be relatively weak. And if you have a weak base, its conjugate acid will be relatively strong. And it's the same idea. For example, ammonia, which is a weak base, its conjugate acid would be NH4 plus. Same idea as F minus. When NH4 plus is in with water, it actually will react with water and donate over an H plus. The result of that is you'll make H3O plus and ammonia. But in terms of the pH of that solution, you now just made more H plus in that solution, and it will actually affect the pH of it and stuff like that. We're not going to do any type of hydrolysis stuff or calculations, but that's the relationship. It's sort of an opposite relationship. So if something comes from something strong, it's relatively weak, its partner. It won't react with water, basically, is what that means. It's considered a neutral salt, basically, is what that means. And if something comes from a weak acid or weak base, its partner is going to basically react with water and can affect the actual pH of that solution, either by making more OH minus or more H plus in that solution. And that's going to alter whether or not that solution is going to be acidic, basic, or neutral. Again, our list of strong acids that we put up there earlier, and we talked about sulfuric acid, which again is a diprotic acid. You could have something like phosphoric acid, which is this guy. That is what is sometimes referred to as a triprotic acid. It actually has 3 hydrogens that will come off one at a time. Is it easier to remove the first hydrogen or the second one, you think? It is actually easier to remove the first one because the first one's neutral, right? And so when you pop that off, the first one, you now have something that has a negative charge and you want to rip something that's positive away from it, it's going to be harder to do so. So it gets much harder to take off each of those hydrogens. When you get to like phosphoric acid, by the time you get to the third one, barely any comes off. Pretty much all of it comes off in the first hydrogen on most of those guys that are diprotic or triprotic. Most of the hydrogen just pops off with the first one. All right, so water, as we talked about, is an amphoteric substance, and we saw it basically as an acid or a base. So in this case, as an acid, and in this case as a base. So it was donating the H plus, and here it is accepting the H plus. Water can actually react with itself and set up an equilibrium, and that's what's happening with water at all times. One water is acting as an acid, the other water is acting as a base, and it will make H plus and OH minus. So this is always sort of happening. The amount of H plus or OH minus that's in the solution is important to whether or not the solution is acidic, basic, or neutral. And that sets up what is known as an equilibrium. And you could actually calculate the H plus concentration and OH minus concentration by using what is referred to as Kw. Kw is the equilibrium constant for water. That's what the W stands for. It equals the concentration of H plus times the concentration of OH minus. And for our purposes, it pretty much is a constant number of 1 times 10 to the minus 14. It really does change with temperature, but your book probably will never change the temperature. So you can think of it in most cases as a constant number. By the way, when you see these brackets, that means concentration. And usually what we're talking about in terms of concentration is molarity, or moles per liter. So that is what we're talking about when we talk about concentration. This can be used to calculate the H plus concentration or the OH minus concentration if you have one or the other, basically. This again is one of the first formulas that, again, as I mentioned, you could swap out the H3O plus for the OH minus. It is the same thing. So good news is the calculation is pretty much the same regardless of which one you're doing. So if you want the H plus concentration, you need to take 1 times 10 to the minus 14 and divide it by the OH minus concentration. And if you want the OH minus concentration, you would take 1 times 10 to the minus 14 and divide it by the H plus concentration. This is definitely the chapter where if you're not using your exponent button on your calculator, you're going to be in some big trouble. Yeah, so you definitely want to make sure you're using the exponent button on your calculator, or you will find yourself getting the wrong answers for sure. Now, we could compare those sort of concentrations. You could think of the H plus concentration as the acid part of the solution and the OH minus concentration as the base part of the solution. So you could actually compare the two, and whichever one is larger will tell you whether or not the solution will be acidic, basic, or even neutral if they're actually equal to each other. So let's talk a little bit about that there. If you calculate it and the H plus concentration is larger than the OH minus concentration, that basically means that the acid part is bigger than the base part, then the solution would be acidic. If you calculate it and the OH minus part is larger than the H plus part, that means the basic part is larger than the acid part. The solution will be basic. And if you calculate it and they equal each other, which means they both will have a concentration of 1 times 10 to the minus 7, then it is neutral. Now, the relationship between H plus and OH minus is this relationship: as one goes up, the other goes down. Yeah, so they go opposites of each other. So if you have more H plus in the solution, you're going to have a lot less OH minus in the solution. And that means it's going to be probably more acidic. And if you have more OH minus, you will have less H plus, which means it will be basic. And obviously, if you have equal amounts, it will be neutral. Any questions on that there? All right, well, grab your calculator and try it. All right, these are all individual problems. So for each of these, calculate either the H plus concentration or OH minus, depending on which one's given to you, and then determine, is it acidic, basic, or neutral? And once again, make sure you're using that exponent button. Yeah. Okay, so let's take a look. And again, in this case, whenever you're given the H plus or the H3O plus, which again is the same thing, or OH minus, you definitely want to think about KW. And again, for our purposes here, it is always a constant value of that 1 times 10 to the minus 14. And the good news, like I said before, really it's the same calculation regardless of which one you're calculating. Again, you're just going to take 1 times 10 to the minus 14 and basically just divide it by the other concentration. The key on this one is, as I mentioned, making sure that you do put it in correctly into your calculator. Again, a reminder of your exponent buttons, right? So you want to make sure that you are punching these in correctly into your calculator. So let's take a look at these here and see what we get. So I'll start with this one here. Actually, that's the second one. So when we do the first one, which is here. So the first one, we do have the H plus concentration. That means we're going to actually do this calculation right here. And that would be 1 times 10 to the minus 14 divided by our 3.4 times 10 to the minus 4. Now, again, when you put this in, depending on which exponent button you got, you probably want to go 1 exponent button, negative button, and 14 divided by 3.4 exponent button, negative 4 in this case, and then hit equals. Again, remember, if you have this combination, you got to put some parentheses around everybody, right? So to use that. And if you do that here, you will end up with a number perhaps. And in this case, you will end up with 2.9 times 10 to the minus 11. You do actually need units since this is a concentration, and typically the units are molarity is what we would use in this case. First off, any questions on that? Now we want to know, is it acidic, basic, or neutral? So what we just calculated was the OH minus concentration, really the base part of the solution. We want to compare it to the acid part of the solution, and we want to know which one is bigger. In this case, which one is bigger? The H plus is larger than the OH minus concentration. A reminder, when you compare exponents, the negative is kind of important there, right? The negative means you're going, in this case, only 4 places to the left and putting zeros. In this case, you're going 11 places to the left and putting zeros, which makes it a much smaller number. So when you're comparing negative exponents, the smaller negative exponent is actually the larger number, right? Because again, if we turn that into a decimal, it looks something maybe like that. We turn this guy into a decimal. I'm going to regret it right about now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 maybe. Yes. And a 2, 9. So much smaller number. Yes. Again, comparing negative exponents, smaller negative exponent is the larger number. Any questions on that? So this guy would be acidic in this case, that solution. By the way, when you're asked that question, there is only one answer. Solution cannot be acidic, basic. I never had anybody go for the trifecta and all three together, but I've had people go acidic and basic for the same solution. So it's got to be one of those 3 answers, acidic, basic, or neutral. It shouldn't be all 3 or all 2 even. Let's take a look at this one. Here again, we have the H plus, which means we're going to do our OH minus, is our 1 times 10 to the minus 14, which is our constant number, divided by 2.6 times 10 to the minus 8. Once again, we want to make sure we punch it in correctly. 1 exponent negative 14 divided by 2.6 exponent negative 8. going to give us 3.8 times 10 to the minus 7 molar in this particular case. Once again, we want to compare our OH minus to our H plus concentration. And really, you could probably just compare the exponents. So that's to the minus 8, that's to the minus 7. That means that the OH minus in this case is actually larger than the H plus. And that would make this solution basic. Yeah. Any questions on that one there? If you find yourself good in terms of your answer for this number, but this number is off by just like 1 or so, it's probably the way you're punching it in incorrectly into your calculator. You're not using your exponent button correctly. By the way, it may not give it to you in scientific notation as well. It may give it to you in decimal form on your calculator as well. So there's sometimes a lot of zeros. You might want to turn it into scientific notation. Continuing on with this example here, the next one was the OH minus given to us. And it doesn't really matter which one's given to us. It really is the same calculation. So once again, 1 times 10 to the minus 14 divided by our OH minus, in this case, 6.2 times 10 to the minus 9. Once again, 1 exponent negative 14 divide 6.2 exponent button negative button and 9. A little equal sign there, and that will get you looks like 1.6 times 10 to the minus 6. Again, we need molarity as is the concentration. Comparing in this case our H plus to our OH minus. Our H plus is to the minus 6, our OH minus to the minus 9. So that means our H plus is a larger value in this case, and that would make this solution acidic in this case. Again, the H plus or H3O plus represents the acid part. The OH minus represents the basic part. Any questions on that one there? Yeah. Last one on this one here, OH minus again. So H plus equals 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. Again, making sure you punch it in correctly. Minus 14 divided by 8.1 to the minus 3. Going to get us a 1.2 times 10 to the minus 12 molar as our H plus concentration. And again, here, our H plus concentration is going to be less than our OH minus concentration, as that is to the minus 12 versus the minus 3. That would mean that the basic part, the solution would be basic as it is higher. Any questions on any of those calculations there? Let's try a couple more, make sure calculators work. Go. Scroll that across the screen here. This ones we just did. Maybe. There we go. Who cares about what the question asks? Let's just say we have an H plus concentration of 2.8 times 10 to the minus 5. What is the OH minus concentration? And is it acidic, basic, or neutral? Okay, so again, in this case, we have the H plus. So OH minus should equal our KW value, 1 times 10 to the minus 14, divided by 2.8 times 10 to the minus 5. So punching it in hopefully correctly here. Gonna get you, looks like maybe a 3.6 times 10 to the minus 10 molar. Again, we want to compare the OH minus to the H plus. So our OH minus is to the minus 10. Our H plus is to the minus 5. Again, the smaller negative numbers should be larger. So that's really all you have to compare is those exponents. So H plus is greater, which means acidic would be a winner on this one here. Any questions on how to do KW? Again, most people struggle with punching it in correctly. So again, remember, make sure that you use those exponent buttons for sure. All right, so now that we know how to calculate H plus, OH minus, we could use that to compare, is it acidic, basic, or neutral? Let's talk about the pH scale, actually, which is a measure of acidity in the solution. And that's not negative, that's just from PowerPoint there. The pH scale actually runs from, dare I say, 0 to 7 to 14 is the pH scale. Less than 7 is acidic. Above 7 is basic. And 7 on the nose is actually neutral. And that's because that's the point where H plus and OH minus equals each other. And that's 1 times 10 to the minus 7. And that would give you a pH of 7, really. As you go from 7 to 0, that's more acidic. As you go from 7 to 14, it becomes more basic. To calculate the pH, that is the formula on the bottom there. This is, again, another formula that you could swap out. pH is equal to minus the log of the H3O plus. So again, you can use it either way. They're basically both the same. You need, as it says, pH means you need the H plus concentration basically to calculate it. All right, let's talk calculators and how to use this correctly. So depending on the type of calculator you got, this formula and the rest of them, you need to go one way or the other. So if you have a display calculator, you're going to punch it in exactly the way it's written, which means you will hit your negative button, you will hit your log button, and then you'll punch the number in using your exponent button. If you have a non-display calculator, this one and all the rest, you need to work backwards. You actually need to put the number in first, hit the log button, and then hit the negative button. How do you know if you have a display calculator or a non-display calculator? Good question. You hit the log button, and if your calculator says log on your screen, congratulations, you have a display calculator. If you hit the log button and it says error on your screen, congratulations, you have a non-display calculator. So that's a quick way to determine which one you have. So if you got log when you hit log, you have a display calculator. You should punch it in exactly the way it's written in the formula. If you have a non-display, you really have to go backwards with all the formulas, depending as to which way you need to go. Any questions on that there? All right, let's try one to see which calculator works there. Let's talk a little bit about significant figures, though, before we do. Significant figures and pH are units like pH, are calculations like pH. The number of significant figures there are in the concentration is how many decimal places you should take the pH value to. So significant figures in concentration to decimal places, not sig figs to sig figs. So sig figs to decimal places. So let's try one here. Let's say you had a H plus concentration of 1 times 10 to the minus 5. Calculate the pH and give the answer to the correct number equation just the way it's written, which means you should punch into your calculator your negative button, your log button. You should go 1, your exponent button, and your negative button again, and 5, and hit equals. If you have a non-display calculator, you should go with the number first, which would be 1, exponent button, negative button, and 5. Then you should hit the log button, and then you should hit the negative button one more time for good measure. Regardless of which one you have, staring at you on your display should hopefully be the number 5, I hope. Yes, that should be what should be staring at you on your display. By the way, it should be positive 5, not negative. It should be positive 5 there, yeah. Now, what should our answer be here? Should it be 5? Should it be 5.0? Should it be 5.00? 5.00000? Feels like a lot of zeros. I'm just going to eliminate that one right off the bat. Which one should it be? It should be this one right here. And that is because when we look at the concentration, which is this number, it has 2 significant figures, which means 2 decimal places, not significant figures in the pH. So significant figures to decimal places, not sig figs to sig figs. By the way, acidic, basic, or neutral, this one? That is acidic. Again, not all 3 answers. So that is acidic. It's less than 7, right? So you should always look. I highly recommend you always look. If you have the pH, you should look at the pH value only. Yes, because if you look at some other values, you may give that answer of it's acidic and basic at the same time, which is not great. Any questions on that there? All right, let's try some here. All right, so for each of these, calculate the pH. And is it acidic, basic, or neutral, each of these solutions? Okay, so let's take a look. And again, the name there, pH, does tell you what you need to calculate it. pH means you do need the H plus concentration. So in number one, we do have the H plus concentration, which means we could just go directly into that equation. And that would get us to pH is equal to minus the log of 2.1 times 10 to the minus 5. Again, depending on your calculator as to which way you want to punch that in, whichever way you choose, make sure it's a good way, right? Or right way. And if you do that, that's going to give us 4.68 in terms of our pH. Once again, two significant figures in the concentration, two decimal places in the pH, okay? Acidic, basic, or neutral, that one. It is acidic. Again, it is less than 7. Now, when we get to question number 2 here, we do want the pH, but we don't have the H plus concentration. We actually have the OH minus concentration. And that means that really, perhaps you should calculate the H plus concentration first by using Kw like we used previously. And if you do that, that is going to give us the same calculation we did previously. 1 times 10 to the minus 14 divided by 5.9 times 10 to the minus 8. That's going to give us an H plus concentration there of too many zeros to count at this hour. Try that. It's going to give us a 1.7 times 10 to the minus 7 molar. Now that we have that, which is the H plus concentration, we could go in there. And now that will be minus the log 1.7 times 10 to the minus 7. I'm going to actually use the whole number, not the rounded number. And that's going to give us a pH of 6.77 in this case. That is going to be acidic, basic, or neutral. Yeah, it's going to be slightly acidic. Yeah. So again, we're going with 7 on the nose is neutral. If it's less than 7, it's slightly acidic. If it's a little bit more than 7, it's slightly basic. Again, because of that. Now, if you did this and you went into the equation with this number here, and you got something like 7.23, you did not calculate the pH, obviously, right? Because you used the OH minus concentration. Good news is you calculated something that's like 2 slides away. That is the OH minus. That's not the pH, but that is what is known as the POH. And you can calculate the POH by doing the exact same calculation, negative log of the OH minus concentration. And it tells you in the name what you need. POH means you need a hydroxide concentration. Why would you maybe want to do that? Well, there's a nice relationship that if you take the pH plus the POH equals 14, which means if you want the pH, you would take 14 in this example minus 7.23. And lo and behold, there is our 6.77 pH that we want without having to use Kw. You could still use Kw like we did, and you get the same answer, or you could actually calculate the POH and then get your pH by subtracting 14. Question on that there. So that does bring up a couple of other sort of variations in terms of how you could calculate certain things. I think maybe we'll look at that just to kind of put it together here to finish up on. We have our Kw, which is our H plus, and our OH minus, which is our 1 times 10 to the minus 14, which again, we could use if we have the H plus or OH minus concentration to calculate the other. We have our pH, which is minus the log of the H plus. We have our POH, which is minus the log of the OH minus concentration. Relationship between that pH plus POH equals 14. A couple of things to add to this is if you actually have the pH, you could actually get the H plus concentration directly from it. And you could get that H plus concentration by taking the inverse log of the negative pH. On most people's calculators, when you hit the inverse log, usually pops up a 10 and a caret and negative pH. Usually on most people's calculator, to get to the inverse log, it's upper left corner, second button or shift, and then your log button, which has a 10 to the x above it. That is how you get to the inverse log on your calculator. By the way, if you have a non-display calculator, you got to work backwards on this one too. You got to start with the number, the pH, make it negative, then hit second log, and you got to work backwards on that one as well. Display, you go forward. POH, you could do the same thing. From the POH, you could get directly the OH minus concentration by doing the same calculation, the inverse log of the negative POH. Again, on your calculator, most people's will pop up the 10 and the caret, and you want to make sure you make it negative. Make sure on all these that you're using your negative button, not your subtract button. Otherwise, you'll get errors. Yes, so negative button, not subtract button, as you do that. One last parting thought here before we take off. pH scale is 0 to 7 to 14. Less than 7, as we talked about, is acidic. Above 7 is basic. And 7, as we talked about, is neutral. pOH scale runs opposite, which means if you're less than 7, you are basic. If you're above 7, you're acidic. And you're still neutral there at a pH of 7. So if you have a low pH, you will have a high pOH and vice versa. This is the exact reason that I said earlier. People give the answer of it's acidic, basic, the same solution, because they'll calculate the pH and go, it's cool, it's above 7, it's basic. Then they'll calculate the pOH and go, cool, it's below 7, it's acidic, the same solution. So do not do that. They run opposite. The pH scale is pretty much the scale most people have in their head. And I would always look at the pH value to determine if it's acidic, basic, or neutral. Again, the pOH runs opposite. And again, one answer for that question.